The investigation that you guys finished earlier in the class, we were looking at the relationship between a length and width of a rectangle and its total area. And we found out with a rectangle that has a perimeter of 24 feet, that the biggest possible rectangle that contains the biggest area, and the area was 36 square feet, but the equation that represented that, which we got to at the very end of that investigation, was y equals negative x minus 6 squared plus 36. Now I want you to notice something about this equation is that the numbers in here, the 6 and the 36, meant something. They meant something in our rectangle. Specifically, the length of 6 feet gave us the biggest area of 36. And what happened was that that point 636 was the vertex of that parabola. The parabola looked like this right here. And that point 636 was the very top of that parabola called the vertex. And it represented the biggest possible area for that particular set of parameters. And so for a length of 6, it gave us an area of 36. What I want you to think about now is that when we talk about this, this is a particular form of a quadratic equation. And it looks very similar to this one down here. This one down here has got this little 15 after the equal sign instead of y. But if we crossed out the 15 over here and we wrote in y equals, let's do it this way. If we crossed out the 15 here and we did y equals, it looks very similar to the one that we have up here. It's not exactly the same equation, but it looks similar. Now, that is a very typical type of quadratic equation, and that is equation what we call written in the vertex form. Right? This type of equation is written in vertex form. The generic version of that, I'm going to put some other variables in here. So we're going to say y equals a times x minus h squared plus k. Now, the letters a and h and k will be numbers when we actually write out the equation. So you'll notice up here, the 2 is in the spot where the a is here, the 1 is in the spot where the h is, and the 3 is in the spot where the k is, or the negative 1 and the negative 3, depending on how you look at it. So those will actually be numbers, but those numbers are going to mean something in these different equations. So we think back to our work earlier this year about dilations and translations and reflections. All those numbers meant something within that context as well. Right? So that's called the vertex form when it looks like that. The other type of form that we're going to look at in this section is one that looks like this over here. So again, if you crossed off the equals 0 at the end and just put y equals on the front, you have an equation. And this is another typical one. You see this a lot in science classes as well with projectile motion. We use this particular equation. And this one is written in what we call the general form. General. Sometimes we use the words general form or standard form. And the generic version, again, will have more variables than you guys might like. I was going to actually switch this over to red here. I noticed I made a little note to myself. So let's say this is in red, just to differentiate it. So we got y equals ax squared plus bx plus c. And once again, there's actually going to be numbers in the spots for a and b and c. X and y will stay in the equation, but there will be numbers in the spots for a, b, and c, and those numbers will mean something. Both of these forms of equations help us to draw the graph, and you know the graph of a quadratic equation is called a parabola. All right, so here are two equations, but they both come from this graph right over here. And you'll notice I've kind of drawn in something here for us. I'm just going to stick that off on the side for right now. But both of these equations right here actually are of this graph. I know they look different, but it's just because they are in different forms. One is in the vertex form. So this one right here is in the vertex form, vertex. form, and this other one over here is in the general form. And they both give us this same graph that you see over on the right here. Just like, when we talked about this before, but you can have fractions like 1/2 and 3/6. They're equivalent to each other and they look different, but they are equivalent to each other. That's basically what we're saying here is these two equations, although they look different, they actually produce the same graph. And we'll analyze that a little bit more later. All right, so label and identify the features of the graph. First off, the vertex. So the vertex of our graph, remember, is, kind of think of it as the minimum value on the graph or the maximum value of the parabola. So in this case, it's a minimum. So the minimum of our graph right here, and I suppose we could label it. Let's label it over here. Let's call it the vertex. And that vertex has coordinate 1, 2, 3, -2. So 3, -2 is the vertex of our graph. Then we have a y-intercept. It's a little bit hard to see on our graph here, but the y-intercept is 1, 2, 3, 4, 5, 6, 7. Actually, it's right here. Let me count that again. 1, 2, 3, 4, 5, 6, 7. If that's actually our y-intercept. So we have a y-intercept, just like in linear equations, our quadratic equations can have a y-intercept, and that y-intercept is at 0, 7. That's the coordinates of the y-intercept. A quadratic equation is only going to have one y-intercept. However, it is going to have oftentimes two x-intercepts. Not always. Sometimes it will have one x-intercept. Sometimes it will have no x-intercepts. But this time, we've got an x-intercept here and here. Now, those x-intercepts are a little bit hard to identify with the exact coordinates. You'll notice that this x value is between 1 and 2, and this x value, let's see, is between 4 and 5. So I suppose we could approximate the x-intercepts for right now as approximately 1.50 and approximately 4.50. We'll have to analyze that a little bit later when we get into factored form. But let me see here. Maybe we can write in x-intercepts, which are right there and right there. So both of those are x-intercepts, and my writing is a little bit sloppy there. I apologize for that. And then the other thing that we are going to have in here is something called the line of symmetry. And now that I've made the other one green, maybe I should change the color on this. But a line of symmetry is basically a line of reflection that you can draw straight down vertically through the vertex. Let's see if I can change the color on that just for our discussion purposes here. Perfect. So that is our line of symmetry. So draw that in. Now, a line of symmetry will always go through the vertex, and it will always have the same value, same x value, I should say, as the vertex. So a line of symmetry is always going to be an x equals equation because it has an undefined slope, and when you have an undefined slope, that'll be x equals, and that means that all the x values on this line of symmetry will all have the same value. So in this case, it goes through 3, an x value of 3. So the equation here for this line of symmetry will be x equals 3. So there's line of symmetry. All right. Now what we'll notice is that some of these are visible in the equations themselves. For example, if you look at the y-intercept value of 7 and you look back up at the two equations here, the one that's in vertex form and the general form, you'll notice that you'll see that 7 pop up as the last value in that general form. So the y-intercept is always going to be visible, or you can see what it is if you look at the general form, and it's always going to be 0, whatever that c value is. Remember c, the reason I'm using the letter c there is because way back up here, that last value in the generic version of the equation, ax squared plus bx plus c, that one is going to be the y-intercept. Whatever that number is, that's the y-intercept. And I put 0 in here because, of course, any y-intercept has an x-coordinate of 0. So this one happens to be 0, 7. The vertex is visible. Would you believe that the vertex, you can see the vertex from the vertex form? Would you believe that? That the vertex would be hidden within the vertex form? It's true. The vertex is visible in the vertex form. And okay, I'm going to use some letters again, so don't freak out. The letters for the vertex will be H and K. All right? So remember, H and K, if I skip to the top of the page, kind of jumped there for a second, I apologize for that. Those two numbers right here and here that are in place of H and K are going to be the vertex of our parabola. Okay? Sorry if I'm skipping around too fast. All right, so the HK values are the vertex, and you'll notice in this example right up here, the vertex values were 3 and, well, -2. In this case, we'll have to talk about a little bit more about that on the backside with why we would say the vertex is +3 and -2, even though you see a minus sign in front of both of those. But those two numbers are the vertex. X and Y value of the vertex. The equation for the line of symmetry, again, comes from the vertex form. So the equation for the line of symmetry comes from the vertex, and we talked about this a few minutes ago when I was writing in the equation for the line of symmetry. It always matches up with the vertex x value. So whatever this is, that is going to be our line of symmetry value. So x, it's always going to be an x equals equation because every vertical line, which a line of symmetry is going to have an undefined slope, and therefore we'll have an x equals equation, and whatever that number is, that's going to actually go in this spot right here. So you'll notice in our example, our vertex was 3, -2, so the equation for the line of symmetry was x equals 3. If this had been 5, -2, then the line of symmetry would be x equals 5. Always works like that.